Okay, so having calculated the viscosity of gases, we're now going to introduce some examples where viscosity is used for calculations. And in order to do that, in general, we would need to go and look at the Navier-Stokes equations. Okay. However, this is a statistical mechanics course and not a course on hydrodynamics. And so these equations here are not going to be our focus. We'll leave those to Barack Obama. He's a clever guy with a lot of time in his hands and he can try and solve them by himself. But we're not going to write down the full Navier-Stokes equations. Well, we all write them down, but then we won't use them. So on the next slide, you'll see we've written them down. Here's the Navier-Stokes equations written down in all their glory. But basically, these equations are this is just MA equals F. And that's all they are, except we're divided by the volume. So there's MA divided by volume and force divided by volume here. But that's what this equation here is. Left-hand side, we can see the mass term, rho. We've got the acceleration term. There's a convective term here. There's a convective term. As particles move through the fluid, this is the velocity of the fluid at any particular point. And so the velocity of the fluid here is a function of r and t, position and time. On the right-hand side, we can see the force terms, the gradient of the pressure, the gravitational force. Gravity might be important in some cases. And this is the viscosity term. Here they've written mu. We would write eta for viscosity, but it's the same kind of term. Now, these equations in principle this particular equation in principle is fairly straightforward, or it would be, except for this nasty term here. You can see the whole thing's linear, more or less, in V, but this term here is not linear, and that gives you interesting effects, in particular turbulence and chaotic motion in general, and that's what makes things so difficult to solve in fluid mechanics if you want to solve things in general. But we're not going to do these equations, not going to use them. Okay. We're, for a start, going to remove all the inertial terms. So all these terms on the left-hand side are gone. Okay. And when you have no body forces, there's no gravity, rho, g, kill it. Okay. No other body forces, no electric field forces. So we end up with this equation here, which balances the viscous drag against the pressure. There's the viscous drag term. This is the pressure gradient term, which will drive the flow. Okay. If you don't have a pressure gradient, you're just solving grad squared V equals 0, which looks like a three-dimensional version of the Laplace equations. Okay. In fact, we're never going to write down these equations because we're going to derive everything from force balance principles. So this, of course, this equation here, these Navier-Stokes equations, are derived from basically force. This is Newton's law. So we can derive everything each time we do the calculation just from first principles. And it's much easier that way. You don't remember an equation. Okay. So the very first system we're going to look at is the very simplest one, which is steady state shear between two plates. So we're going to take a fluid here. There's our fluid. I'm moving this in here. Liquid or gas, doesn't matter. The bottom plate here is fixed. This top plate is moving at speed v. Okay. Distance between the plates here is h. There's the distance between the plates. And we're going to take a layer of fluid between y and y plus delta y. So y is this direction here. Y is the up direction here. So this is y, and this is y plus dy. And I'm going to look at a layer of fluid just in here. What's happening to it? Okay. Now, what's happening to it is that it's flowing along at some velocity. Here it's given by u of y in this diagram. And we're going to look at the forces on it, basically. So what we derived is the momentum current. So the momentum current in the x direction, okay, there it is, okay, is given by flowing out. Let's have a look. Flowing out of our layer is j of y plus dy. So there's a momentum current in this direction. Flowing out of here. Okay, and that momentum current is j of y plus dy. And there's a momentum current flowing into it from below, which is j of y. So that's the momentum in the x direction, but we're looking at the flow in the y direction of that momentum. Okay, so it's a bit confusing, but you have to put up with it. Okay, so And we know from what we've derived previously that J of y plus delta y is equal to eta dv dy, the velocity gradient. So the velocity at any point in the fluid is v here rather than u, so let's call that v. Okay, eta dv dy at the layer here at y plus dy. Okay, and similarly, the momentum flow into the system is given by, from the bottom, is given by minus eta dv dy evaluated at that point at y. Okay, so we've got those two kinds of systems here. Let me go through that again. Okay, so we've got here a layer, and we've got momentum flowing out of that layer, but the momentum we're considering is in this direction. Okay, and that's minus eta dv dy at that point there, and there's also a minus eta dv dy flowing in momentum current evaluated at that layer. Okay, so therefore the total momentum per unit time into our area, per unit time per unit area into our volume, is given by this: j of y in minus j of y plus dy out, which is minus dj dy. Now we're going to assume we have a steady state situation, so that means no time variation. Okay, and in that case, we can't have any forces acting on our layer. If there were forces, then of course you get accelerations. So we can't have any forces acting on our layer. That means the rate of momentum change of our layer must be zero. So therefore, dg dy, dj dy times dy is equal to zero, or the same thing as dj dy is zero. Okay, from here. Okay, but we also know that j is minus eta dv dy. Okay, and therefore that means that eta dv dy must be equal to a constant, just integrating that equation once. Okay, and then to solve it, we want to know what the velocity profile is. That's our aim here. I didn't go into that, but that's what our aim is. We know at the base of our layer, at here, the velocity is 0, and here the velocity is big V. So we have our bounding conditions, because basically the fluid must stick to the plates. Okay, no slip. That means the no slip boundary. This is no slip at the boundary. So V at y equals 0 is 0. V at y equals h is big V, the velocity of our top plate. So you can just solve this particular differential equation and integrate again, and you get Vx as a function of y is the velocity of the top plate times y divided by h. So it just increases linearly as you go between the plates. V equals 0 here, and it goes up to V. Just like a parallel plate capacitor, it's exactly the same system. Okay, so that's what the velocity profile looks like. Now in fluid mechanics, we introduce something called the strain rate. Okay, we have a velocity profile looks like this, and the quantity V on h, which is that, has the dimensions of 1 on time. You know, velocity has dimensions of length divided by time, and then we're dividing it again by h, which is length, so it's 1 on time. Okay, and this thing is called the strain rate. It's normally written as gamma dot, there's a dot there, and it's equal to V on h. So we can write things in terms of the strain rate if you wanted to, which is the velocity profile is equal to the strain rate times how far you are from the bottom plate. Okay, that's that equation. Now, the viscosity doesn't appear in our equation. So if we look at the velocity profile, even though I said we're going to use the viscosity here, the velocity profile just doesn't have here, doesn't have a sigma, an eta, I mean. However, that doesn't mean it's completely disappeared. The quantity minus eta dv dy, which we took as a momentum flux, is also the stress. It's a force per unit area. It is the force per unit area which each sliding layer exerts on its neighbour. So that's another way of deriving this. This thing is a force per unit area, but it's a shear force. It's parallel to the planes. Okay, so in our geometry, this is a constant. Okay, because dv dy is just gamma dot. Okay, so the shear stress is equal to minus eta times gamma dot. Okay, so everything here is a constant. Eta is a constant, and gamma dot's a constant in this particular geometry. And this is the force per unit area which the fluid exerts on the plates and vice versa. So you ask how much force does the fluid exert on the plates? Well, it's this per unit area. How much force does the plate exert on the fluid? Exactly the same. Okay, so that's our stress. Okay. So where does the viscosity comes in? Well, it comes in obviously from the stress. So we've got this equation which definitely involves the viscosity. The more viscosity you have with the same strain rate, the greater the stress. But I'm moving the top plate here. So here's my plates, and I'm moving this top plate at speed v. Okay, and it has on it a force per unit area which is that. Okay, so I've got a force I have to apply, which would be eta gamma dot times the area of my plate. So I've got a force, I've got a velocity. This implies that I have to apply some kind of power. Okay, I'm dissipating power in doing this. I can't just do this for nothing. Okay, so the power per unit area, which if I'm sliding the top plate, I'm putting into the fluid, is just the velocity times the force per unit area, which is therefore the velocity times eta times gamma dot. So the viscosity occurs again, which you can also write as eta v squared divided by h, the distance between the two plates. However, I'm applying a force and I'm using up some power doing this, but the fluid does not accelerate. We're in a steady state. So what happens to the energy? Well, it dissipates as heat. Okay, that's what we've got heat being generated here. So the power per unit volume dissipated is just going to be the power, which is this thing, okay, divided by so this is the power per unit area. So this thing here is where are we? Let's get rid of this thing so I can see it. This here is the power per unit area, and the power per unit volume I need to divide by h, the distance between the two plates, to get the power per unit volume. So the power per unit volume is this, which you can also write as eta gamma dot squared. Okay, and that's a general result for the case where the velocity is in one direction and the gradient in the velocity is perpendicular to it. That's true in our case. Okay, so the power dissipated per unit volume in our particular case is this, where you have the velocity is in one direction and the gradient of the velocity is perpendicular to it. Okay, now so that's the power per unit area, and you can see that involves directly the viscosity. Okay, now a question for you to consider is, in our gas derivation for viscosity, we don't appear to have introduced any loss mechanism, any way of converting the thing into heat. But obviously we have somehow, so it's up to you to figure out which step allows us to do that. It seems to be lossless, but in fact I've just told you it's not lossless, and there's a power per unit area which is dissipated as heat, and it's that. Okay, so let's do a numerical example. So take honey. Typical honey has a viscosity of 10 Pascal seconds. That's the unit. Pascal seconds would be the unit. We have a two-plate system. Again, let's do two plates. Separated by 1 centimetre. So we've got 1 centimetre there. The area is 1 metre squared of each plate. Okay. The top plate's moving at 1 metre per second. Okay, everything's 1 except for the viscosity. What is the force on the top plate? Well, the force is just area times stress. Stress is force per unit area, which is area times eta times the strain rate, which is V on H. If we do the calculation, we find the answer is 1,000 newtons. Okay, that's quite a lot of force, really, 1,000 newtons if you think about it. That's not completely trivial. Okay, so what is the power dissipated as heat? Okay, we can do that two ways. We can say the power input is the force times the velocity on our plate. The force is 1,000 newtons. The area of a plate is 1 square metre, so the force is the power is 1,000 watts. I'm putting 1,000 watts into it. Or alternatively, I can integrate this over the entire volume, and that gives that result, which in fact is the same answer, of course, because that's how we derive things. Now, 1,000 watts is a pretty big number, and that's sort of equivalent to an ordinary radiator going sort of at half capacity, roughly. If we did this for a while, the honey would quickly heat up, and we'd get a decrease in viscosity, of course, as the honey heats up, and we get less power dissipated until we reach some steady state, or the honey starts to vaporize eventually, probably boils away. All right, second problem is another very classical system, probably the second most simple system you can consider. but a very important one, which is Poisson flow. So flow in a pipe. So we've got a pipe, radius r, length delta L, here it's L, but it can be delta L. Uniform pressure drop delta P along it. Okay, so the pressure drop along this pipe of delta P. So delta P is like P2 minus P1 here, if you like. Okay, and we want to find two things. The velocity profile of the fluid along the pipe as a function of the coordinate r. So I want to know what the velocity looks like as a function of r. If I go out, the velocity here is pointing that direction. And I want to know here the volume of fluid flowing down the pipe. Here it's a bit different to the previous problem because in the previous problem I was just shearing the top plate. Here I've actually applied a pressure gradient along the pipe. And I want to figure out, okay, for that pressure gradient, how much fluid do I get flowing per unit time? It's like, normally the system of water distribution in cities, you have a hill with a water tank on top of it. You have some pipe coming down and distributing it to all the houses down here. I want to know, given the pressure gradient from here to here, what flow I'm going to get. It's a very classical problem. Very useful. Originally, the physics of this would have been worked out probably for fountains and things like that, but the fountains and aqueducts and such things. Okay. So Poisson flow in a pipe. How do we do this? Well, what you do is you do another force balance. Okay, so we've got our flow in our pipe, and we consider an imaginary cylinder of fluid within the pipe of length L. So let's have fluid of length L, and let's look at the forces on it. Okay, so at either end of our imaginary cylinder, so here we've got an imaginary cylinder, it's radius r, length L. So I should put radius r here, radius r. So here we've got out to radius r, little r. We've got a pressure force on either end, and we've got an area here. That's the area of our end, so it's the area of one end there. And we've also got a pressure drop across this. So this is length L. Then the pressure drop across the pipe is L dp dl. So that's the gradient. That's fixed. So this gives us the pressure drop. This thing, in other words, is P2 minus P1. If you call that P2 and that P1, if we're flowing in that direction. Okay. So you want to know that the actual force on this, it's basically P1 times the area minus P2 times the area, which gives us that result there. Okay, that's the two forces due to the pressure at either end. And also we have a drag, and the drag on this particular cylinder is caused by all the fluid around it slowing it down. Because remember, at the outside the pipe here, the velocity must be 0. Inside the pipe we don't know what it's going to be, but at the out boundary it's going to be 0. So you know it's going to decrease as you go outwards. Okay. The viscous force all around the curved portion of an imaginary cylinder is just the curved surface area, 2 pi RL, times the stress. Okay, force times force per unit area times the area gives you the force. So the stress is the force per unit area, so it's minus e to the VDR. So the force we have is just the multiplication of those two things, and that's the force on our pipe due to the viscous drag effect of all the other bits of the flow. So we're just balancing two forces here. The pressure forces are balanced against the viscous flow. And when we do that, we just equate them, we end up with that equation there. Okay, this thing here is a constant. Okay, it's our pressure gradient. Okay, eta is also a constant, of course, as well. Integrating, we note that the boundary at the end of the pipe, not the end of the outside of the pipe, at r equals big R, velocity is 0. Okay, so we end up with this, which is integrating once, and we get that. Okay, that's our profile of the velocity as a function of radius. It's parabolic, and it does, of course, depend upon the viscosity, okay, and upon the pressure gradient. All right, so it's a parabolic profile, maximum in the middle. Right, how do we get the volumetric flux? Okay, the volumetric flux is how much fluid per unit time is going down the pipe. Okay, the volume, that's the volumetric flux, so the volume per unit time. Volume per unit time flowing down the pipe, and that's what you want to know if you've got a water distribution system. You know, how much flow am I getting out of this thing? Well, it's pretty easy. I just integrate over a whole series of annuli. So I'm in cross section here. Here's my cross section of the pipe. I'm going to integrate over the annulus between R and R plus dr, and the flow through that annulus is 2 pi R dr times VR. And then I integrate that over the whole pipe, and I end up with this result here. Again, it depends upon the viscosity. If the viscosity goes up, I get less flow. If the pressure gradient goes up, I get more flow. Okay, but the crucial thing here is this R to the 4th term. So the flux is proportional to an incredibly high power of the radius of my pipe. And that means very thin pipes produce almost no flow. A larger pipe that's 10 times the diameter of the thin pipe will produce 10 to the 4 more flow. Okay, now that has many applications in all kinds of industrial things and all kinds of biological things. You know, you want a lot of flow, you just increase your pipe by a little bit and you get much more flow. Okay, this, I should point out, always assumes we don't have turbulent flow. We have laminar flow. Okay, there's nice layers sliding across each other. But within those restrictions, and normally you don't want turbulent flow for cases where you want to deliver fluid, because turbulent flow tends to stop the delivery of fluid. It tends to break things down. So the major application, or one major application of this, is in blood flow in people. Okay, so if you've got coronary artery disease, what happens is your arteries delivering blood to the heart start to block up. You know, now if you've spent your entire life living on a diet of ice cream and lard and God knows what else, and you don't do much exercise, your arteries will slowly develop plaque and they'll build up fatty deposits. And you might say, oh, well, it doesn't matter very much because, if my arteries get blocked by, say 50%, who cares? I'm 65 years old. I don't really care very much. I'm not going to run too many more marathons. Okay. The problem is, if you reduce your radius by 50%, you get a blood flow reduction of 94% because of the R to the 4th effect. Okay, and that means that if you do try and survive on a diet of ice cream and other fatty foods, and you don't do much exercise, you're going to die very quickly. And so this is one of the reasons why you'll find a lot of physicists exercise a lot, because they know you can't beat nature. This R to the 4th thing will eventually terminate you. Okay, and on that very positive note, I will end this lecture. Thank you.